And the third one is goes with this one of the physical question. It can be from electrochemistry, ionic equilibrium, gases, thermodynamics, anything. So here they are going with a little different thing, that is with the ionic equilibrium, which is very straightforward as well. So we will quickly go through this. So first of all, I will stop sharing because I want to give you the description in the board, and then we will study about how to approach this question. Okay. Meanwhile, if you have any question, you can post. Right. So they have given Y is weak acid. Right. So we have a Y solution Y, and its concentration is given 1 m, and its pH is given 3.00 and 25 at 25 degrees Celsius. So 100 cubic centimeter of the sample solution was in a shaking bottle. Okay, so basically we are going to do a layer separation here. So there will be Y here. The volume is 100 cubic centimeter, and there is an organic solvent, and its volume is also 100 cubic centimeter. Okay. After shaking the bottle, it was placed in water baths. So they are trying to maintain the same temperature. Thereafter, the two layers were separated. Yeah, that's okay. The aqueous layer was labeled as solution Z. So this is the initial condition. And let's say at equilibrium, so we have the layers separated here. So there will be this acid HA that is dissociated in between this aqueous and organic layer. Okay. And now this aqueous layer, they have named this as Ez, which is the after equilibrium condition. And they have taken 25 cubic centimeter from Ez because this volume is 100 cubic centimeter, which is used here. And they have now titrated this with 0.5 m NaOH using phenolphthalein. So there is no problem here because this is a weak acid and this is a strong base. So your indicator should be in the basic region, which is phenolphthalein, which is very good. And the volume of NaOH required is 40 cubic centimeter. Okay, so this is the story, right? Then, right, so, okay, so this is clear, right? So you have the initial condition. This is at equilibrium, and this is 25 cubic centimeter from the equilibrium aqueous solution, and they are titrated using this. Right, so then we will discuss about the question. The first question says calculate the degree of dissociation alpha, okay, of the weak acid solution in solution Y at 25 degrees Celsius. So they are talking about now only this solution Y. So solution Y, you know, they have given the pH, and they have given the concentration, and they have given the volume that they have used. You have to find the degree of dissociation. Okay, it is alpha. So what is normally happening here in Y? So you have HA acid, right? So I will stop sharing. So here you have HA acid, which is going to be dissociated H plus and A minus. Okay, since they are going with the degree of dissociation, it is easy when you are also using this degree of dissociation alpha, because degree of dissociation alpha means how much of HA is dissociated when you have 1 mole of HA. So basically, if you have 1 mole of HA, how much is going to dissociate? This is 1 minus alpha. Okay. So this is the amount that will be remaining at equilibrium if the dissociation is alpha. And this is alpha plus plus. Okay. And this is the number of moles that is going to be dissociated from 1 mole. Okay. To find how much in terms of concentration, you need to multiply this by concentration of the acid, which is going to be C, and here this will be C alpha and this will be C alpha. Okay. So this is how you can go with directly with the degree of dissociation. Otherwise, you need to go with the normal method. You take this concentration as C and you take the dissociated amount as X. So this will be C minus X, this will be X, and this will be X. And based on the pH value, they have given 3.0. You can calculate the H plus concentration. So this will be 10 to the power minus 3m. But remember, you have to show that. You have to very small show that pH is 3. So H plus concentration is minus log H3O plus concentration is equal to pH. Then you can plug pH 3.0 and find the value of the concentration of H plus is 10 to the power minus 3. And then you can understand from this part, your 10 to the power minus 3 will be C alpha, because there is a concentration of H plus. So you know C alpha is 10 to the power minus 3m. Right? So alpha is equal to 10 to the power minus 3m over, what is the concentration of this here? It is given that as 1m. So basically you can say your alpha is 1 over 1000. 10 to the power minus 3 means 1 over 1000, which gives you the idea if you have 1 mole of this HA, only 0.001 mole of HA is going to be dissociated, which is very, very minimum. But remember, still it is given pH 3. It is acidic. Okay, this amount of dissociation, degree of dissociation is enough to give this acidity, pH 3. Okay, so that is very important to identify. Okay, so this is the easiest way that you can go with the degree of dissociation if you have alpha that is asked. Otherwise, you need to consider about this one, and then you need to tell X is the concentration of H plus. Then you need to find X using Ka. Okay, now the idea is you don't have Ka, but you know the concentration of H plus. So you can write down in the concentration of H plus is 10 to the power minus 3m in 1 decimeter. Then you need to find the number of moles of H plus in 100 cubic centimeter. Then you can find the number of moles of X in 100 cubic centimeter. So basically this will be 10 to the power minus 3m, 100 into 10 to the power minus 3 decimeter. Okay. Then you know the number of moles initially from HA. It will be the 1m. So this is in 1 decimeter. Then you can find this in 100 cubic centimeter. So 100 into 10 to the power minus 3. Okay. So you can understand how much X is formed, H plus is given out, and you can find the amount of HA initially present. So it will be 100 into 10 to the power minus 3. And here this will be 100 into 10 to the power minus 6. And your alpha will be the dissociated amount 100 into 10 to the power minus 6 over the initial amount 100 into 10 to the power minus 3. So you can cut this and you can find this is 10 to the power minus 3. Okay, so this is a long process. If you are going with the moles, not moles directly, the concentration, right? But if you are going with the moles and degree of dissociation, this becomes very straightforward. You can find alpha in 2 steps, very easy, right? If you are going with the concentration, first you have to find the number of moles dissociated and what is the initial amount. Then you can have the ratio between the dissociated and initial amount, which is the degree of dissociation. Okay. Right. So this is for the first part. So what is asked in the second part? We will check. And you know now the alpha, calculate the dissociation constant Ka of the acid H. So this becomes straightforward because from this equation, if you write Ka it will be H plus concentration, A minus concentration, which is C squared alpha squared, and C1 minus alpha is equalized to alpha. So this will be C alpha. So you can cut this. So basically, Ka is equal to yeah, this is equalized to 1. So basically, K is equal to C alpha square. So you know the concentration, that is 0.1 m. No, it's 1 m, the initial concentration. And now you know alpha is 10 to the power minus 3. So here it will be 10 to the power minus 6. So basically, Ka will be 1 into 10 to the power minus 6 m. Okay. So you can show Ka is equal to H plus concentration times A minus concentration divided by HA concentration. But please remember, you need to put all physical states. And here also, when you are plugging into the equation, HA in the bottom, so you need to put H plus concentration equals A minus equals concentration, HA equals. Okay. Then you can show this equation, K is equal to C alpha squared, and then you plug alpha to find K. Okay, so you will get K is equal to 1 into 10 to the power minus 6. Now this is a first level question that we normally discuss in pH calculation and all those things. Okay, so this is done. Calculate degree of dissociation alpha of the acid HA in solution Z at 25 degrees Celsius. Now here the case is, the situation is little bit different, right? Because you can understand now, they are now asking about the degree of dissociation alpha in solution Z. So what is solution Z? Sorry. So solution Z is this after the equilibrium. Okay. So when the layers were separated, they have taken 25 cubic centimeter and they have titrated with 0.5 m NaOH. So can you find the amount of acid that is present here using this? Because when there is HA in this reaction medium, HA will be reacting with NaOH to form actually Na plus water. So if you know the amount of NaOH that is consumed, basically, you know the amount of HA that is present in the aqueous phase in principle. Okay. So I will stop sharing. Okay. Right. So you can find the number of moles of NaOH here. So it will be, so I will erase this now to make it clear. Okay, so you can find the amount of HA that is present here. So NaOH number of moles is CV. So concentration is 0.5 m, 40 into 10 to the power minus 3. So basically 40 into 5 means 200. So 20 into 10 to the power minus 3 moles. So this much of will be present in 25 cubic centimeter. Don't forget, this is in 25. Okay, but here Z solution is 100, which is 4 times. So you can write down therefore number of moles of HA in 100 cubic centimeter. First, you can write down NaOH is CV, and this is equal to NHA in 25 cubic centimeter. And therefore, NHA in 100 will be 80 into 10 to the power 3 moles. Okay, so this is the amount that is going to be present here. 80 into 10 to the power minus 3 moles. Okay. So this is straightforward. So now you know HA. So again here in solution Z, there will be HA that is undergoing H plus A minus. So you know the amount of HA that is present. So this will be the initial amount, the total amount of HA that is going to be present, the concentration. So you can find the concentration 80 into 10 to the power minus 3 mole, basically the same concentration that is here. And the volume is 100 cubic centimeter 10 to the power minus 3. So basically this will be 0.8 m. Okay. No confusion, right? 20, yes, 80 into 10 to the power minus 3. Then the volume is 100 into 10 to the power minus 3 decimeter here. Yeah, so this is the concentration that is present in the Z aqueous solution. Then what you can do the same equation that we used before. So now you know we have already found Ka. So Ka is equal to C alpha squared. So Ka is 10 to the power minus 6. So the initial concentration here in the HA solution, the total concentration is 0.8, and you can find alpha squared. Okay. So alpha squared will be 1 over 0.8 into 10 to the power minus 6. And you can get the root to find the alpha value. This will be 10 over 8, which gives 5 over 2, 5 over 4. So it will be like 1.25 root into 10 to the power minus 3. So which is important in the next question. See? So basically you found here the amount of NaOH that is present in 25 cubic centimeter, because we use here the titration. And you find the amount of HA in 100 cubic centimeter based on the calculation. And if you know the amount of HA, this will be the total amount of HA in aqueous phase. Okay. And you know that then initial concentration, you can divide it by the volume to get the initial concentration. So this is 0.8 m. And then if you know 0.8 m, we have already calculated Ka. So you can use Ka is equal to C alpha squared to find alpha. Okay, so that is straightforward. So you have found here alpha dash, and here you have found alpha. So using the values of alpha and alpha dash calculated above, comment on the relationship between the degree of dissociation and concentration of the acid HA at 25 degrees Celsius. Okay, so what do you think about the degree of dissociation here? That is very important to understand, right? So here you can understand alpha dash and alpha. So here I think we calculated alpha. Initially, question number 1. Wait, I will check. Give me a second, because I want. So this was just to make sure. Where is it? Yeah, 10 to the power minus 3, and here alpha was where is it? 1.1 10 to the power minus 3. Yes. So here you can understand this was 10 to the power minus 3, and here it is 1.1 into 10 to the power minus 3. So here this is straightforward, because you have to just take the root of this value, 1.1 to 1.25. Then, so you can understand what is happening here. Okay, so 10 to the power minus 3, and here 1.1 10 to the power minus 3, and here the concentration, the initial concentration was 1 m, and here the concentration of HA that we found is 0.8 m. Right? So what can you comment on this? That is what they are asking. Comment on the relationship between degree of dissociation and concentration of the acid. So the easiest thing that you can comment here is, when the concentration of the acid is decreasing, degree of dissociation has increased at 25 degrees Celsius. This is important. You have to mention the temperature as well, because they are maintaining the temperature 25 at each case, and you are comparing two situations. Okay, So the comment is, you can see the alpha is increasing. So basically the degree of dissociation has been increased. The dissociation is increased when the concentration is decreased. So that is the idea of this particular question. Okay. Then it becomes very straightforward. So calculate the partition coefficient at 25 degrees of the HA between water and organic solvent. The weak acid HA does not dissociate or dissociate in the organic solvent. So we have to give that, or you have to use that assumption anyway. So we have to disregard the dissociation of HA in the aqueous medium for this particular part. Okay, don't forget this particular part. Okay, because we already know the amount of HA in Z, right? So I will stop sharing, because we already know the amount of HA in Z. Right? So we already know this is the amount. 80 over 10 to the power minus 3 mole was HA in Z. And now they are telling for this particular question, forget about the dissociation. Because in the previous question, we did the dissociation and we found the alpha. It is a different value than the previous case. And here they are telling, forget about the dissociation just to find KD. Okay. So they are trying to give us KD, HA concentration in water. So they have given, trying to find the partition coefficient between water and organic. It doesn't matter that you find between organic and water, but here they have tell about between water and organic. So I'm going to find like this, organic, right? So you know how much H2O is, HA is present in H2O. This is 80 into 10 to the power minus 3 mole. And you know the initial amount. So initial amount will be CV, so it will be 1 into 100 into 10 to the power minus 3. So the initial number of moles is 100 into 10 to the power minus 3. So after equilibrium, there is 80 here in the aqueous phase. So how much that is went here? 100 minus 80 is 20 into 10 to the power minus 3 moles. Okay. So the concentration of HA at H2O phase is 80 into 10 to the power minus 3 over 100 into 10 to the power minus 3 decimeter over HA in organic phase is 20 into 10 to the power minus 3 moles. You can put moles over 100 into 10 to the power minus 3 decimeter. So basically all these will be cut and your answer will be 4. And if you use HA organic on top and HA concentration of H2O on bottom, this will be 1 over 4, which is 0.25. Okay. But here in the question, they have to find the partition coefficient between water and organic. So this is the most suitable answer. 4.0. You can write down 4.0. Okay. Okay. So HA between water and organic. Okay. You can write down in different ways, in the both ways, but preferred one is between water and organic solid. Okay. And then finally, calculate the pH of a mixture containing 25 cubic centimeter of solution of Y and 25 cubic centimeter of solution of NaOH. So this is actually not relevant to this particular question, like the entire question, but they need to fill the marks. So they have given another part. So you have 25 cubic centimeter of Y. So this one. So you know the concentration of Y is 1 m. And you have 25 cubic centimeter, and then you know you have given 0.5 m NaOH. So we will quickly discuss that one, so without taking much time, because all these are theory. Okay, don't forget these are just theory. There is not much to think. I will tell in places where you have to think a little bit. Okay. So the idea says, I will share my screen for myself. So you have, okay, so you have 1 m. Y means it contains HA aqueous. So you have 25 cubic centimeter of this. Plus you have NaOH. So basically this reaction is going to happen. Na plus H2O. And how much you are going to add? 0.5 m, 25 cubic centimeter. Okay. So what is actually forming here? Think about this 1 m, 0.5 m. So automatically you see this will be remain, this will be the limiting factor, and this will be formed here. So what is this? What is this? You can answer this question I am asking. What is this solution? What is forming here? Please use the chat box to explain, or just tell me what is this solution that is going to form here. You have HA, which is the weak acid, and you are going to add a strong base. And you can see according to the stoichiometry, there will be here 25 into 10 to the power minus 3 moles. And here with NaOH, you will have like 0.5 into 25 into 10 to the power minus 3, which is half of this. And all NaOH will be consumed, and 0.5 into 25 into 10 to the power minus 3 HA will be remaining, and 0.5 into 25 into 10 to the power minus 3 will be of NaA is formed. So what is this solution? Quickly answer. What is this solution? I am waiting for your answers. What is this solution? Very quickly. Yes. Yes, it's a buffer solution. Yeah. So you can see weak acid, and a part of the weak acid, the conjugate base, is remaining here, right? So primarily, this is a buffer solution. And you can directly use the Henderson-Hasselbalch equation here. So primarily what you have to do here is, so according to that, this is the initial. And at the final case, you will have 1 m 25 into 10 to the power minus 3 moles minus this 0.5 25 into 10 to the power minus 3. So there will be no NaOH remaining. And here, the same amount of NaOH that is consumed is going to form here. So this will be 0.5 25 10 to the power minus 3 moles. And you know the Henderson-Hasselbalch equation, pH is equal to pKa log salt concentration over acid concentration. So you know Ka 10 to the power minus 6. So basically you know pKa, this is 6.00 plus log salt concentration you can put here over the total volume is now 50 into 10 to the power minus 3. And here also the total volume is 50 into 10 to the power minus 3. So you can plug this value here and plug this value here. The only thing that you don't know is pH. Okay, so you can find pH using that. These are just straightforward theoretical questions. Okay. Right, so we'll move on. So this is done. Okay. Question number 3 is also done. So we will move on to